Hi, welcome to video for section 1.2. This video is going to cover methods of enumeration, or more basically put, it's going to teach us how to count. The first thing we're going to learn in this section is the multiplication principle. And the multiplication principle can be used to count the number of ways that multiple events could happen together. So, for instance, to start off, we'll say, suppose that E1 is an event that has N1 possible outcomes. And another event, E2, is an event that has N sub 2 possible outcomes. Then the number of ways that E1 and E2 could happen together can be found just by multiplying the number of ways E1 can occur, N1, times the number of ways event 2 can occur, N sub 2, and that gives us our total size of the outcome space for those two events. So, for example, a food truck sells taco platters, which include a taco with beans and rice. Customers may choose between beef, chicken, pork, or vegetarian tacos, and customers may also choose between black beans and refried beans. So if we want to say, well, how many possible ways could a customer order a taco platter? Say, well, there are 1, 2, 3, 4 ways we could order a taco, times 2 ways they could choose beans, which gives 8 possible ways that a customer could order a taco platter. So that's a multiplication principle with just 2 events. We can actually extend this to more than 2 events. If we consider M events, E1, E2, up to EM, such that each one has a number of possible outcomes denoted by N sub I for event I. Then the number of ways that those M events could occur together can be found by just multiplying the number of ways event 1 can occur by the number of ways that event 2 can occur, and continue to do this process until we've multiplied by all the number of ways that the mth event can occur. So again, another example. When ordering a Happy Meal at McDonald's, customers choose an entree, either a hamburger, cheeseburger, or chicken McNuggets. They choose a drink, milk, chocolate milk, or apple juice, and they also choose a side, apple slices or yogurt, and in addition, all of them come with French fries. So if we want to say, well, how many different Happy Meals are possible? We've got 1, 2, 3 possible entrees, times 1, 2, 3 possible drink choices, times 2 possible side choices. So 3 times 3 is 9, times 2 gives me 18 possible Happy Meals. So next we're going to start talking about something called permutations. A permutation is just an ordered arrangement of different objects. And if we want to figure out how many ways we could arrange n different objects, that would be the number of permutations that are possible. So we think we've got sort of n objects, so it means we're going to have n sort of slots to put them in. And if we want to think about, well, okay, how many possible choices are there to put in the first slot? I've got n objects, and any of them could be put in the first slot. So I'd have n factorial, n just n possible objects that could be chosen for that first spot. Now when I move to the second spot, I've already used one of my n objects, so I only have n minus 1 choices left. There are n minus 1 possibilities for that second slot. The number of possible outcomes left for that third slot, I've used up 2, so I've got n minus 2 possibilities left, and so on. Once I get to the last slot, there's only going to be one choice left because all the other n minus 1 objects have already been placed. So if I multiply, use the multiplication principle, say how many ways could I place these objects, you can see that the number of ways that I could permute them is n factorial. And just to refresh people's memory, if you haven't worked with factorials in a while, if I have n factorial is defined to mean n times n minus 1 times n minus 2 and so on until I get down to multiplying by 2 and by 1. Okay, so just kind of keep multiplying. And other thing I just want to remind people is that 0 factorial is defined to be equal to 1. Sometimes people forget that. So permutation would be an ordered arrangement, remember? So if I want to say, well, how many ways can the letters J-U-M-P be arranged? Say, okay, well, I'd have 4 possibilities for the first spot, 3 for the second, 2 for the third, and 1 for the last one. So since I have 4 letters, the number of ways that I could arrange them would be 4 factorial, which is 4 times 3 times 2 times 1, which would give me 24 arrangements. If instead of arranging all n of the objects, I wanted to just take some of the objects and arrange them. I want to think about how many ways I could arrange r out of the n objects when r is a smaller number, or at least not more than the total number of objects. In this case, I'm going to be choosing r objects. So I've got 1, 2, 3 up through the rth slot to fill. I have n objects that I could choose from for the first slot. So there are n possible ways that I could fill that slot. When I get to the second slot, I've already used up one of my n objects, so I've got n minus 1 left, and so on. When I get down to the rth object, I've got n minus r plus 1 objects left that I could potentially choose from for that spot. If you want to kind of see that, let's just look at the third slot. We'd have n minus 2. So you can see for each slot, we're taking n minus the slot number plus 1. Right? I say, okay, n minus 2 plus 1 would be n minus 1. N minus 3 plus 1 would be n minus 2. So n minus r plus 1 is why we get that number there. And so we could write this as n factorial divided by n minus r factorial. And that's how we can count the number of possible ordered permutations of r out of the n objects. And the notation that we use for that is np r. So it's the number of permutations. P is for permutations. N is the number of objects. And r is the number selected. So I'll do another quick example. I'm coaching a softball team with 16 players, and I need to create a batting order that includes 10 players. So if I want to think about how many different batting orders could I form from the 16 team members. So here, the total number of objects. The objects are the team members. So I've got n equals 16. My batting order is going to be an arrangement of 10 of them. R equals 10. I know that in softball batting order, the order is important. Who bats before and who bats after each person, not just who's selected to be out on the field and in the batting lineup, but which order they bat in is important. So this is why I want to count the permutations. So I would choose to have 16 P10, and I take my n factorial, 16 factorial, divided by n minus r factorial, n minus r, that'd be 16 minus 10 factorial. So that gives me 16 factorial divided by 6 factorial to get the number, whoop, sorry. I said 6 factorial, but I wrote 16. 16 divided by 6 factorial gives me the number of possible batting lineups that I can come up with. Let me stop for 1 sec. Okay. So when it comes to actually calculating this on the calculator, I'm going to use a TI-84 to just show you how you can do this. There are a couple of different things you could do. First of all, if I want to take, I've got 16 factorial divided by 6 factorial, so I could go to the math button. So let me go here. Do 16, and then math, and then I can go down to the factorial, and then divided by 6, math, go over to probability, and go down to the factorial button. So I can now press enter, and it tells me 2.905, 94304 times e to the 10th power. So that's a very large number of possible batting lineups. Just to show how we could do this directly without calculating the factorials, we could also use the math button and go to probability. Actually, let me clear out of there. I think I need to do 16, then math, and then say I'm choosing 10, and that also calculates the number of permutations for me. So if I want to use the permutation button, I put in my n, again 16, then I press the math button, scroll over to probability, go down to the permutations, that's number 2, click enter, and then put in the number of objects that I'm permuting, 10, there we go. Okay. So we talked about permutations being ordered selections of objects, right? Ways that we could put objects into an order. When we're not concerned about the order, but we're only concerned about which objects would be selected, that's when we're talking about a combination. So a combination is an unordered selection of objects. So if we want to think about how many ways can we form a combination of R objects out of N objects. So really we have a large group of N objects, and we're trying to figure out how many ways we could form subsets of size R. So we know that the number of ordered arrangements is our number of permutations. And then if I think about how many ways, want to divide that by the number of ways those R objects could be arranged once they've been chosen. So if I take that and divide by the number of ways the R objects could be ordered. That's going to be R, PR, the number of ways I can arrange those R objects. This is going to give me n factorial over n minus r factorial is the number of ordered arrangements I could make. The number of ways those particular R objects could be ordered is R factorial. So the number of ways I could form unordered subsets is going to be just doing this division, n factorial divided by n minus r factorial times r factorial. And the notation we use for this calculation for the number of possible subsets of size r that can be made from n objects, we use the notation n choose r, C for combinations, n again is the total number of objects, r is the size of the subset, and there is alternative notation that's sometimes used for this. In addition to n choose r, this is sometimes written with parentheses, with n up at the top and r down at the bottom. So to do an example, how many 5-card poker hands can be formed from a standard 52-card deck? The order doesn't matter. Which card is dealt to me first, second, third, fourth, or fifth is not important. All that's important is which cards end up in my hand. So since order isn't important, I just want to know how many different subsets, how many different hands are possible. So here, n is the number of objects that I'm choosing from. So those are 52 cards. R is the size of the subset, so I'm looking for a 5-card hand. So to answer the question, I can calculate 52, choose 5, which is going to give me 52 factorial divided by n minus r factorial, 52 minus 5 factorial times r factorial in the denominator, 5 factorial, and this will give me 2,598,960 different 5-card poker hands that are possible. And if we want to look at how to calculate this with the calculator, once again, I can use the formula directly with factorials. I could say 52, go to the math button, and choose the factorial, divided by (52 minus 5 is 47). Go to the math button, factorial times 5, again to the math button, factorial, and it gives me my 2,598,960. I could also do this directly with the math button. I'm doing 52, choose 5, so I do 52, press the math button, scroll over to probability, come down and select NCR, enter 5, and I get the same answer. So just making sure people are comfortable doing these calculations with your calculator. It's very difficult to try to do them other ways, so you want to make sure you know how to do it efficiently. so now we're going to talk about sampling with replacement versus sampling without replacement. When we sample with replacement, what that means is that when an object is selected, it is then replaced afterwards before the next object is selected. So ultimately, sampling with replacement, what that means is that each object may end up being sampled more than one time. And so if we want to think about how many ordered samples of our objects are possible, if we're sampling from n objects with replacement. So if we're sampling with replacement, and I'm going to take a sample of R objects. I've got R slots that I'm going to fill. That's my sample. And for the first slot, I have n possible objects that I could choose. Everything's available in the sample. I choose one of them, and then I put it back in before I choose again. So when I go to make my next selection, again, I'm going to have n possible objects to be selected. And the same thing will happen after the second selection is made. That object that was selected will be put back in, and so every time we make a selection, there are always n possible choices. So looking at the total number of ways we could make our selections in this case, using the multiplication principle, I'm going to have n to the rth power is going to be the number of ways that I can choose a sample from n objects of size r if I am making my sample choices with replacement and I care about the order. So let's see. Now if I'm sampling without replacement, sampling without replacement means that an object is not replaced after it has been selected, which means that each object can be selected only one time. So if I'm sampling without replacement, and I want to know how many ordered samples of our objects can be taken from n objects if I'm sampling without replacement, this, remember, is back to the situation where I have r possible slots to fill. For the first one, I have n possible choices, but since I can't choose the next one, the next choice I make, I've lost whichever one was chosen first. I'll only have n minus 1 choices left for my second slot, and so on. N minus 2 choices possible for the third slot, and n minus r plus 1 possible for the rth slot. So in this case, the number of ordered samples that could be made if I take samples without replacement is going to be that familiar formula for the permutation. Right? N factorial over n minus r factorial. I'm just kind of coming back. And then the last thing I want to talk about is the idea of distinguishable permutations. If I consider the letters in the word Ohio, if I consider them all to be different, right? And I thought about how many ways I could permute the letters, right? So I've kind of labeled the O's as being different here. Then I could figure out how many possible permutations I have and say, okay, well, let's see. I'm permuting the 4 letters into 4 places. So I have 4 factorial equals 24 possible permutations of the letters. And I can see here are my 24 possible permutations of the letters. But when I have 2 O's, unless I label them specifically, really if I were just looking at whether I have an O, an H, or an I, not all of those permutations are distinguishable from each other. I've got 2 of each type, you can see. Right? Because I've got 2 different ways I could place the O's. Right? And if I weren't distinguishing between them, then these would really be the same. So if I want to think about calculating the number of distinguishable permutations, what I need to do is I need to look through it and say, okay, I need to divide by the number of ways I could arrange the letters that are indistinguishable. Right? So in this case, since I have 2 letters, my O's, that are indistinguishable, I'm going to figure out the number of distinguishable permutations. I'm going to take the number of total possible permutations divided by the number of ways to arrange the indistinguishable letters. So in this case, since I have 4 factorial total possible permutations, and I have 2 ways that I could arrange the O's, I really only have 12 distinguishable permutations. So when we're referring to distinguishable permutations, this is what we mean. Okay? Now, in general, if I have n objects, and I have n1 of one type, and n2 of a second type, and so on. So I've got n sub s of the s type, such that if I add up all these values, n1 plus n2 up to n sub s, that equals the total number of objects n. The number of distinguishable ways that I could permute these objects is going to be equal to n factorial, that's the number of total permutations, divided by the total number of ways that I could permute each type. So that's n1 factorial is the number of ways I could permute the objects of type 1 times n sub 2 factorial gives me the number of ways I could permute the objects of type 2, and so on. I'm going to multiply by all the n's up through n sub s factorial. So, for example, if I were looking at how many distinguishable permutations can be made with the letters in the word mathematics, I can look through it. I can say, okay, well, let's see what I have for letters. I have letters of type M, and I've got 2 of those. I've got letters of type A, and there are 2 of those. I've got letters of type T. How many T's? There are 2 of those. I've got letters of type H, and I've only got 1. I've got letters of type E, and there's only 1 of those. Let's see, A, M, A, T, I already have those. I've got letters of type I, and I've only got 1 I. I've got letters of type C, and I've got 1 of that type. And I've got letters of type S, and I've only got 1 of that type. So just looking here, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 total letters. So our N is 11, and if I add these up, we've got 2, 4, 6, 7, 8, 9, 10, 11. The sum of these do in fact add up to my total size. And so if I want to think how many possible permutations are there that are distinguishable, I will take my 11 factorial, right? My n factorial is 11 factorial, divided by m factorial, a factorial, t factorial, and so on. But notice that when I've only got 1, each of the ones that I only have 1 of, 1 factorial is equal to 1. So if I multiply these by 1, it doesn't change anything. So what I really need to do is I need to go through and I need to say, okay, which of these values have, which of these types have more than 1 of them? It's the M, the A, and the T. And I need to take my total number of letters and divide by how many M's I have, 2 factorial, times how many A's I have, 2 factorial, times how many ways I can permute the T's, 2 factorial. And so this will give me my total number of ways that I can distinguishably permute the letters in mathematics. So as I said, I could multiply by n sub h factorial and m sub e factorial and all that on the bottom too, but I don't really need to because when I've only got 1 of those letters, I'd just be multiplying by 1, by 1, by 1. So again, just doing this in the calculator, at this point I need to say, okay, I've got 11 factorial, 11 math factorial, divided by, now I've got 2 factorial, times 2 factorial, times 2 factorial, and that will give me my answer, which is 4,989,600 different ways that we could distinguishably permute the letters in the word mathematics. It's kind of surprising, isn't it? It seems like an awful lot of different ways. So it just goes to show you that when you start, even with relatively small numbers of things, the number of possible ways that things can be arranged becomes very, very large quickly. So hopefully these examples and definitions will help get you started with counting. There are lots of practice problems to do in the book. Keep in mind that there is homework to do, that you should be doing all of the homework, and you will need to post the solution to your assigned problem on the group discussion board by Sunday. Remember that you should also be discussing your classmates' solutions with them, but that otherwise the homework is ungraded. It's the quizzes that you'll take, and those will become available at noon on Sunday and are due Tuesday night, which are going to be your graded assignments for the week other than being graded on participating in that discussion board. Have a good day.